Hi, everyone. Welcome to Waste 360's Nothing Wasted podcast. On every episode, we invite the most interesting people in waste, recycling, and organics to sit down with us and chat candidly about their thoughts, their work, this unique industry, and so much more. So thanks for listening and enjoy this episode. Hi, everyone. I hope you enjoyed this episode. This was a session that we had at the inaugural Sustainability Talks at Waste Expo, and it's awesome. It's with Brian Staley of EREF, and he has such a great way of distilling science into understandable bits of knowledge for all of us to understand and think about and digest. And the beauty of this session is a lot of us think that, oh, what's the point of recycling if it all is mixed together, or what happens at the end of life? And this science session really digs into that and uses data and other pieces of scientific information to really share that and show us the importance of that and the importance of science in sustainability, especially in the waste and recycling industry. So please give a listen. Hope you enjoy it. And we hope to see you at Sustainability Talks at Waste Expo this May. Thanks.
Take the floor.
Great. Thanks so much. So, as Stephanie alluded to, what I'm going to talk about today is the science of sustainability, specifically focused around waste and recycling. So before we get into the detail of this, I think it's important to frame the broader concepts of what sustainability means. So the point here is that our mere existence, the fact that we are alive, living, and breathing, results in consumption of resources. So conceptually, though, sustainability would be meeting the resource and services needs of the current and future generations without compromising the health of the ecosystems that provide them. And so that's the broad concept of sustainability that I would argue most of us are familiar with. I think where things get interesting is when we start thinking about this in terms of actionable items. Our actions do have consequences. Our actions have environmental costs or burdens, which can detrimentally impact long-term sustainability. So efforts to improve sustainability are actions that reduce these costs or burdens, ideally to a zero burden, although I would argue that's not always possible, or if it is possible, it's at a significant cost in other areas of society. But examples of some of these burdens would include things like water use, energy use, litter in oceans, waterways, and elsewhere, smog, acidification, toxicity, things of that nature. So when we think about these consequences and putting that in the framework of sustainability, it's okay, we know we're going to have consequences, but if those consequences can get remediated or can be better over the longer term, that's what we define as sustainability, because then things are sort of prepared for future generations. An example of that would be pulling water out of a lake or a pond, for example, and using that for drinking water. So if we pull a certain amount out and that pond or lake is able to refill, then that's sustainable, right? But if we pull so much water out that pond is drained and no longer is able to sustain the folks that are drinking that water, that's unsustainable. And over the long term, we don't know whether or not that would have some substantial consequences. So that's one example of how actions can have consequences that sort of plug into that sustainability framework. So the big question is, when we think about these different consequences, which I'll call environmental burdens from here on out, really the overarching question is, which of these are most important? Because all of these are burdens, and some of these potentially are more important than others, depending on where we live, depending on the framework that we're operating under, and what we're able to control, quite frankly. So the relative importance of these becomes a part of that conversation when we're talking about overall sustainability and what kinds of consequences our actions have. So what does that mean in practice when we talk about sustainability? So practically, sustainability efforts need to be demonstratable, they need to be actionable and quantifiable in order for us to be able to evaluate that kind of progress. So some examples that I pulled from things that are out there today related to sustainability and specific actions that we could take to improve sustainability. And some of these are perhaps better than others, again, depending on which burden we're talking about. This is a depiction of saving water. So, for example, this is reducing a burden around water use, but that doesn't necessarily affect something like greenhouse gas emissions. So these are just examples of some of the specific action items around a specific burden, which then has a relative impact. Conserving energy, for example, reducing CO2 emissions by riding a bike. And we're going to talk about nuance a lot in subsequent slides here, because these are very sort of binary kinds of activities. If I ride a bike, I'm going to reduce CO2 emissions. Not necessarily, because some of there were CO2 emissions that were generated in order to construct that bike. So if you purchase a bike and you only ride it 5 minutes a day, it becomes questionable as to whether or not you're actually reducing CO2 emissions. Now, if you ride it every day and replace your commute in with your car with a bike, that's a different story. The point is that there is nuance in a lot of these topics of conversation around sustainability. And I think it's important that all of us understand those nuances, because it's only in the nuance are we able to actually create real change and be able to measure that change over time. That gets back into the area of waste and recycling. Recycling, reducing, reusing, those different concepts. And then the concept of zero waste. Again, there's a lot of nuance in this, and we're going to go into an example around what some of the nuance is, specifically around recycling here in just a bit. But this kind of gets into what I'm alluding to. Is how can we be sure that these activities are beneficial? How do we quantify that in a way that ensures that we're doing this stuff, maybe we're feeling good about it, but ultimately, are we doing more harm than good, or are we doing more good than harm? And that becomes one of the key constructs in order to assess the actual true measure of sustainability, is making sure they are beneficial. And how do we measure that? And so let's get right into that right now. One common tool that's been increasingly deployed about understanding and measuring sustainability is through the concept of life cycle assessment. So this is a framework that examines, identifies, and evaluates environmental burdens, such as things like energy use, material usage, environmental implications of various processes, products, or systems across the lifespan of that from cradle to grave. And it would look something like this, very much kind of a mass balance accounting sort of approach. So you've got inputs coming into your system, such as raw materials, you're putting energy into that. An example would be making bottled water, or making your favorite snack food, or something else, whatever consumable you want to think of. And then once you input those raw materials and that energy, then you have the manufacturing of that material, the usage of that material, and then ultimately there would be some discard at the end that needs to be managed. So on the output of this life cycle framework, you've got things like emissions, waterborne waste, solid waste, co-products, and other kinds of things. So this is the LCA is the construct that's used more and more commonly as a way to kind of account for these environmental burdens that I've just alluded to. And that's a way then to assess how sustainable our efforts actually are as it relates to some of our actions. So let's get into kind of a case study then and evaluate what this means a bit more. I'm going to use recycling, since recycling is arguably the thing that most people tend to think about when we start talking about sustainability, specifically as it relates to waste management. So when we apply the concept of life cycle assessment, it provides a scientific approach that can help answer some very specific questions about recycling, such as, why do we recycle in the first place? When does recycling make sense? Is there ever a situation where recycling doesn't make sense, for example? What materials should we recycle versus what materials perhaps maybe we should not recycle? Can recycling be worse than landfilling? How can we improve recycling? So evaluating the operational capabilities or limitations help understand the likelihood that recycling is effective and that the LCA results can be achieved. And that's an important aspect to consider, because when we think about recycling overall, it is certainly important, if you're going to apply something like a life cycle assessment, that we're clear on what the definitions mean. And so I alluded to an operational aspect of recycling. And I think that's critically important, because it's not just the scientific aspect of can we recycle this? And if so, like what are the material attributes and the engineering attributes that allow this to be recycled? But it's the operational aspect of things too, because the reality is that there are aspects of what happens that are really outside our control in some respects. That's where the operational components have significant impacts. So for example, the definition of recycling based on science and operations would say that these are materials that can be reprocessed directly into the same materials and used again. So plastic would go back to plastic, for example. Paper would go to paper, and so forth. That would broadly include primary commodity recyclable categories such as fiber, cardboard, paper, so forth, metal, your steel, your aluminum, plastic, PET, HDPET, and glass. So an example of what that would not include would be something like composting, for example. Composting would not be considered recycling because if you compost a material, it is being converted into some other product. So in this case, if you're going to compost, say paper, for example, paper isn't going back into paper. Paper is being composted and being used as a soil amendment, which is different. So and there are different facilities that manage these kinds of operations. And so from a science and operations standpoint, you can frame the definition of recycling or other aspects of waste management, but in this case, recycling, around the idea of the scientific components as well as the operational components. Now, certainly if we think about these commodity recyclable categories, there are exceptions in these categories, particularly in the fiber and plastics area, which that's a conversation for a different time. Now, let's get into some of the science of this now. So this is a graph from a study that EREF conducted not that long ago that evaluates the different classes of recyclable materials. You've got your glass, your aluminum, your ferrous, and your plastic and your fiber here down on the x-axis. And on the y-axis is your assessment of greenhouse gas emissions impacts. And so the way to look at this is that anything below this zero line means that you are having a less emissions you're having compared to landfilling that material. So if it's negative, that's good. If it's positive, that means there are more emissions compared to landfilling that material. So you can see right away that there's a range here with each of these materials. The white dot represents the average, but the blue bar represents the variability across the United States as it relates to recycling. In this case, glass is what I'm pointing at. So this would suggest, for example, for glass, that since some of the blue bar is above zero, that means there are situations across the United States where recycling glass is worse than landfilling. Picking on aluminum, we see the entire blue bar is below zero. That means there are virtually no circumstances based on this assessment that would mean that aluminum is better to landfill because it has higher emissions from the recycling side of things. So the point here is that there is variation across these different materials when they're recycled that can result in situations where recycling it is more detrimental than simply sending it to landfill. And the reason that you see this variability are some things that are really out of our control, such as the energy grid we're in. So that the variability here is not constant. I think the key takeaway here is different recyclable materials have different sustainability footprints for a particular environmental burden. This is greenhouse gas emissions. Let's look at these same materials for energy use. Now, if we look at energy use, a different environmental burden, you can see that these materials perform, for the most part, really, really well. Just about all of these bars are below the zero, with the exception of ferrous, but it's just a little bit above that. So this would suggest that if the environmental burden we are discussing is energy use, then that means that most of these recyclable materials perform really well. If our environmental burden that we're interested in is greenhouse gas emissions, then we have to look at this a bit more closely because it is variable. It is variable, particularly for fiber, for example. You can see a huge range here, and that's based on the different kinds of fibers that are out there and the different end uses. So point here is not all recyclable materials are created equal. This is some of the nuance I was alluding to earlier in the presentation. Now, There's another concept I want to bring into this, and I mentioned the idea of science and operations in defining recyclability. And so I would break that down a little bit more and describe recyclability as a function of the material characteristics and the operational characteristics. So I frame this in terms of material recyclability and operational recyclability. So material recyclability refers to the recyclability of the actual material itself, such as the ability that cardboard can be reprocessed back into cardboard or another type of fiber. Now, this particular attribute is required in order for a material to be recyclable at all. You have to have material recyclability. In other words, if you got a number one plastic, that number one plastic grade is what you need to recycle it. But then if you think about that number one plastic, let's talk about operational recyclability, because just because it's made out of a number one plastic does not mean that it will necessarily be recycled. So operational recyclability refers to the likelihood or potential that a recyclable material will actually be recycled. So for instance, using that number one plastic as an example, we'll say a water bottle. If I am in a certain area of the United States or Canada or elsewhere that does not have a recycling program, for example, and does not accept recyclables, then the likelihood that that bottle is going to be recycled is actually quite low unless I'm willing to transport it somewhere else where there is a MRF or a recycling infrastructure in place. That's an operational component. The material configuration of that plastic, for example, comes into play too. Is it a flexible plastic grocery bag, or is it a rigid bottle, for example? Different recyclability potential. Most places don't accept plastic bags, for example, into formal recycling programs. You have to specifically take it somewhere different. But that plastic bottle, most will take all day. The material use, is it coming into contact with food, or is it a medical use? For example, medical exam gloves, plastic exam gloves. While the plastic may be very recyclable because you're using, the way it's being used is for medical exams, it's typically not very attractive or not able to be recycled. Or uncaptured materials like litter. Consumer behavior is another big one. Is it recognizable by the consumer to be recyclable? If it's not, or if it's questionable or it's confusing, then most likely you end up having low operational recyclability for certain materials. Classic example would be gable top containers, multi-laminate materials in some cases, and other things like that cause confusion for consumers. The availability of the infrastructure I already talked about, whether or not there is a recycling program that's there, and that strength of end markets becomes into play as another key part of the operational recyclability. Because if the markets aren't there, even though it may go through a MRF, the markets aren't there, it's not going to happen. I mean, we've heard stories in the past of areas that recycled a lot of glass, but because of the end markets were extremely weak, sometimes that glass ended up going to landfills because there was no one who would take that glass within a reasonable distance of the MRF. So that's yet another example of operational recyclability. So what do we do with this? And how do we look at this from that standpoint? We're thinking about recovery efficiency. We're thinking about recycling rates. This is data from the US EPA since the 1960s. And you can see the recycling rate trends have generally been up until recently. Over the past few years, we've seen a dip. But my point here is that this trend graph basically is a representation of both the material and operational recyclability components that are out there. This is really kind of the embodiment of what that means. So the obvious question then becomes, all right, so how high could we realistically get this number? And there is a ceiling, if you will, on how much we realistically can recycle right now. And there are various reasons for that. Some of it is based on these different operational components. Some of it is, based on limitations at the MRF, based on consumer behavior elements and so forth. But I'd like to identify a couple of drivers that could raise that ceiling. And we've done some work on understanding like how much could we realistically recycle today, given what we know. And what we found is that roughly the maximum recycling rate we could conceivably achieve using commodity recyclables only as our way to assess that is around 50%. So what's holding us back? What's keeping us from going into those higher percentages? Well, there are a couple of key drivers, I think, that can help influence that and increase that moving forward. One is technological advancement. We're seeing that right now with the advent of increased use of artificial intelligence in MRFs, for example. that are more efficiently able to sort out materials, able to pick out those recyclable materials. And of course, that also has different benefits over time too. The better those machines get at sorting materials, then conceivably the more efficient that sorting is at the most level, which means we should be able to have a higher capture efficiency of those recyclables. Then you've got some of the more futuristic aspects of chemical recycling, green chemistry, other ways that we can create additional usable industrial materials or industrial chemicals from some of these materials that could be recycled and go that direction. Then you've got, which I think is probably right now anyway, one of the most important potential impacts that we could see that can help enhance recycling is that of product manufacturing. We think about it, it's the product manufacturers that ultimately deal the cards to the waste management entities. They can only accept what goes in the trash bin or the recycling bin, and that all is based on the design decisions that product manufacturers are making. So if packaging can be designed with strong end markets, strong demand, that's going to help close the loop much stronger fashion than if the packaging design is weak and that results in those materials having to go elsewhere and not close the loop. Creating demand by using those recycling materials, the product manufacturers can make a commitment to receive more materials that have been recycled rather than using virgin materials. And then considering how the packaging design may impact the end-of-life metrics. This kind of goes back to the LCA evaluation. Does the packaging design result in an end use that is better than another end use? And if so, how do we understand then what should happen from a product manufacturing design decision? So let me give some examples to kind of illustrate what I'm talking about here. So this is an example of the end uses of PET. And so if you look at this from an end use standpoint, I'll draw your attention to the upper right side of the slide here. About 41% of recycled PET ends up as fibers. So think of clothing, carpet material, so forth. About a third goes back bottle to bottle, which is what we would historically call full-on closed loop recycling. Bottle goes back to bottle, that's closed loop. PET sheets, strapping tape, and so forth. The point is the majority of the PET, if we're saying that bottle to bottle is closed loop, the majority of PET recycling is not closed loop. So what does that mean? Well, if we look at this graph on the left side of the slide here, this shows that the reduction in greenhouse gas emissions drops substantially depending on where the end use is. So bottle to bottle clearly has the highest reduction in greenhouse gas emissions. But if you go to fibers, and depending on the different kinds of treatment for fibers, you can have a very small reduction in greenhouse gas emissions. And we're not even talking about these other uses. This is just fiber and bottle to bottle. So the point here is that the end use really can matter. It can have a significant impact. We can't just assume that if something is recycled, it's going to go back to the same use or the same material that it was before. So this tells us that we can't make that assumption that if I recycle a plastic bottle, it's going to go back to a plastic bottle. Only a third of the time does that happen. So that means it's very important to understand what the environmental burdens are for these other end uses. And I think this next slide really highlights the potential impact that end uses can have. This is using glass as an example. This is a study out of the UK. Forgive me, I don't have the reference down there. I did not translate that over. But this is a study out of the UK that evaluated different end uses of glass. And the important part here is that when you think about these end uses on the x-axis, you've got glass containers. So this is glass container back to glass container, closed loop. You've got some other closed loop attributes here, but I really want to call your attention over to the right side of the graph. When you get to using glass in bricks, in shot glass for filtration, or in aggregates, you see that those uses, and aggregates would be for road subbase and things like that. What you see here, at least from an emission saving standpoint, you actually go negative, which means that it's far better to put the glass in a landfill than you would using it for these end uses. Key point here is that there's a lot of variability depending on what the end use of a particular recyclable material is. And that end use needs to be evaluated if we're really going to understand the true sustainability metrics. So for instance, we can have a situation where glass is being used for filtration. That's the worst negative impact, for example, right? Glass is being used for filtration. If the purpose of using the glass for filtration is to be more sustainable. Well, this would suggest that's not at all what's happening. In fact, it's worse. Far better to landfill the glass than it would be to use it for filtration if the goal is greenhouse gas or CO2 emission savings. So end use of materials is key to realizing the potential environmental benefits. That's a key part of understanding the nuance of it. And unfortunately, right now, there's a lot of information out there that really isn't getting into those kinds of details. So the larger public is left to believe that as long as I put this in a recycling bin, it's all good. Now, certainly, it's not necessarily up to the public to determine where this end use goes. But if companies are making decisions and it's part of their ESG goals, for example, they want to ensure that you've got that greenhouse gas emission savings. This becomes an important part of that environmental social governance structure, so that you can understand when it makes sense to send something to one particular end use versus another. So let me give a couple more examples of end-of-life trade-offs, because I think it's to me, it just helps seat that in my head a lot better when I can see these examples and kind of understand in what situations potentially does this make sense and does it not make sense. So this is a styrofoam cup from a fast food restaurant. And the concept here is I want you to take a look is what's being said here on this cup. This says that this styrofoam is shown to biodegrade 92% over 4 years under simulated landfill conditions. And so let's pick that apart a little bit. Okay, so that's what the cup says. Now, what happens in reality? Well, when someone throws this cup away, most styrofoam would typically go to a landfill. So they're on the right track with the kinds of testing to represent a simulated landfill condition. Most waste to landfills goes to landfills where landfill gas is being collected, and that's good. A lot of it is being used beneficially to create heat, to create energy, so that's good too. But the testing says the cup will go away about 4 years in a landfill. Is that good? Well, let's think about that for a second. So in a landfill, here's a depiction of a landfill gas collection system in the lower right. So you've got these underground gas collection pipes, you've got your gas wells, the gas is being collected, it's being transferred over here to this blower system, ultimately to a generator, you're making electricity, it's all good. Okay, so sounds great, right? So when we think about it though, when are we putting these gas collection systems in place? In a very aggressive sense, most landfill gas wells are installed between 3 to 5 years after the waste is placed in there, right? More closer to the 5-year side of things, but generally speaking, within 3 to 5 years, that's when these gas collection wells are getting installed. So if this material degrades, most of it, 92%, over less than 4 years, what's happening to that gas if these gas collection wells are not installed yet? Well, it becomes fugitive emissions. So in that respect, even though this suggests that this is a good thing, in practice, with what we know about when gas collection wells are installed, we actually don't want this to degrade in less than 4 years. It would be far more beneficial for this cup to degrade in 5 to 20 years, so that gas could be captured and used for electricity. So this is an example of where we've kind of got this situation where testing is being performed. It sounds like we're doing good. We're going to degrade 90% over 4 years. But maybe that's not the case. Now, these are an optimal lab-based condition, so I'm going to throw a bone to this particular test method. The reality is, when you put something in the field setting, in an actual landfill, it is going to take longer than 4 years for a lot of it to degrade. But the point is, this suggests that the testing doesn't really comport with the actual operation of a landfill. So there needs to be more information in order to really demonstrate that putting a styrofoam cup in a landfill that degrades like this is going to behave in a way that's actually going to achieve some sort of sustainability benefit. So again, nuance becomes key. Let's look at another example. So that was a biodegradable styrofoam cup. Let's broaden this out and talk about biodegradability in general. So when should something be biodegradable? That's the overarching question. What does biodegradable mean? Well, most definitions would say that if something's biodegradable, that means the material should break down in less than 1 year. So you would have something that would look like this in the span of a year. This bottle's here, and then it goes away into something that's just tiny particulates. So when we think about that, that's good, right? Because otherwise, if it doesn't biodegrade, we end up with a situation that might look something like this, the whole ocean plastics problem. Well, this material is now in the ocean, it doesn't degrade, and so it just keeps building and building, and we've got these big garbage patches. So that's a significant problem. It is a significant problem. So that would suggest then we should design all this plastic to be biodegradable so that, that way if it doesn't end up in a landfill, it's going to degrade and all is good. And so I think this is an example where we have some trade-offs to think about. So again, going back to the styrofoam cup, let's think back about what happens in the landfill again and when gas collection systems are installed. And since most landfills, most of the waste now exists in landfills where they're converting gas to energy, this goes back into the framework of, okay, so if this degrades in 4 years or less, and it's being properly disposed of in a trash can, and then ends up in a landfill, is that good that it's degradable there? Well, it's definitely good if it biodegrades in the environment, but what if it's properly disposed of? So the question is, should packaging be designed to minimize environmental impacts when it's properly disposed of, or when it's improperly disposed of? Okay, so if the plastic bottles then go away in the ocean, so we've helped address the ocean litter problem. But if those same plastic bottles degrade in a landfill in that short period of time, then that potentially creates more emissions. So the question is, which environmental burden are we trying to address here? And sometimes those burdens can compete with one another. In this particular case, it becomes an issue of creating more fugitive emissions, which over the longer term create potentially a more detrimental impact to the environment, or dealing with the ocean litter problem today, knowing full well that we still may have to address a longer term environmental problem that we're creating by making something like a plastic bottle degradable. So this just highlights some of the nuance and some of the conversations that are ongoing, both in the scientific circles as well as the policymaking circles. So some of the key implications now to sum all this up. Not everything can be recycled. Recyclable materials do have different sustainability impacts based on some of their different attributes. Non-recyclable waste materials do have to go to the other endpoint at this point in time. I wish we could turn everything directly into energy, like we've seen in some of the movies, but that's just not possible right now. So that means that even though we want lots of things to be recycled, or composted, that certain things still need to go to other places. The other thing is in terms of maximizing sustainability at end of life. That currently typically means looking at the upstream packaging design, making sure it syncs with available endpoints, enhancing the sustainability of all endpoints and not just recycling. And so I'll end with this as an example when I talk about enhancing all endpoints, because in reality, when we talk about making one particular product or consumer product more sustainable, that one product doesn't exist by itself in a vacuum. In reality, the entire waste management infrastructure in North America and elsewhere really is an integrated system. So that's, in that respect, we need to evaluate, well, how does this work practically speaking? So in some areas of the United States, we potentially have a one bin system, just one bin, everything goes to a landfill. Less and less frequent, but there's still some places like that. Most areas of the US have a two bin system where things are being landfilled and recycled. And then those same areas, many of them have a yard waste type of collection accessibility. So that's a three bin system. And then in some of the more progressive areas, you may even have a four bin system where the food waste is being collected separately and composted. So EREF did a study that evaluated these different options across the United States to understand what would be the different benefits. And what we found was kind of interesting. So this table depicts your 2, 3, 4 bin system as well. This says 3 bin, but this is yard and food waste, so that's the 4 bin that I showed in the previous one. This shows your emissions. So again, the larger the negative number, the better. And then we've also got landfill diversion rate, because it's typically stated that we need to divert more from landfill. That's going to be most sustainable. So what we found was interesting, because if you look at what's the most negative number, so that's the most reduction in emissions we can achieve, is with a 2 bin system, but the diversion rate, the highest diversion rate we can achieve, was not with a 2 bin system. So this suggests a disconnect between the idea that the more we divert from a landfill, the more sustainable we're going to be. What this suggests is that diversion rate should not be a consideration when we're looking at maximizing sustainability of an integrated waste management system. That really doesn't correlate. So we have to look at it more from an integrated standpoint to really assess the value, and from a sustainability standpoint. So a higher diversion doesn't correlate to greater emissions reductions. That's a key finding that really hasn't been, I think, strongly enough emphasized, and it's a fairly new finding, so it's not surprising that that's the case. So lastly, on the road ahead, there are lots of things that need to happen to continue to advance sustainability around waste and recycling. The most important thing, and I know this sounds a bit trite coming from a research organization, that more data and research is needed, but it really is in this respect. There are a lot of data gaps right now that exist to help us understand things around end uses, markets, increasing the accuracy of some of these LCA analyses, looking at considerations like emerging contaminants and so forth. Consumer education is always key. Obviously, if we can do more from a technological standpoint, from a design standpoint, we can really help that consumer education piece, but it's still very important. And then leveraging what we find from that data and research to help inform decision making. That's critically important. But again, back to the concept of nuance, and I'll end here. It's really critical in the entire conversation to make sure that we understand some of the nuances so that we can really ensure that we know operational limitations have significant impacts on the practicalities of whether it's recycling, composting, or otherwise. And in nearly all situations, the concept of sustainability really isn't a binary conversation. Science is advanced enough now for us to understand that it's not a black and white. There's a lot of gray in between, and there are trade-offs in many of these situations. And so with that, I will thank you for your time and appreciate being a part of this conference.
Thank you for listening. It would mean the world if you would take a moment to rate or review this podcast. And if you share it with us on one of our social networks, we are giving out some fun, nothing wasted podcast swag. So just tag us and see what you get. Thanks so much.